My name is Joey Murphy. Um, I am a rising fourth year graduate student at UC Santa Cruz, where I work with Natalie Battaglia, doing radial velocity follow-up observations of transiting exoplanets discovered by NASA's TESS spacecraft. And I do a lot of this work with Faye, actually, too. And today I'm going to talk to you about the radial velocity technique, sort of in general. What does it mean when you hear people that do exoplanet research talk about radial velocities or RV analysis, and why it's useful? I'll talk about some of the technical tools that we'll need to have sort of a familiarity with in order to make radial velocity observations useful. And through all of this, I'll be introducing you to this Radvel Python package, which is a code base that you can use to analyze radial velocity observations. Okay, so I'm not going to go through, as we go through this notebook, this Jupyter notebook, there will be spots where you can sort of fill in the blank, and we'll go through the kind of outline of this notebook and work some of the examples. But I'll leave some of those fill in the blanks empty for you to maybe try on your own. So yeah, first of all, what do we mean when we say radial velocity or the radial velocity technique or method? So there are a handful of introductory resources here that I really encourage you to go and check out. Anywhere from, a more formal kind of white paper to give you an introduction onto the radial velocity technique. Also, we have resources for some of the technical tools that we'll talk about, like periodic gram analysis, and also Markov chain Monte Carlo methods for error estimation. But just getting back to the scientific picture of like what do we mean when we're talking about radial velocities? So this is a very useful GIF that I think is painting the picture for us. So if we look on the left panel, look at the left panel of this GIF. Imagine we're staring at a star with our telescope. So here's our telescope. We're looking at this star that's far away. And say that star has a planet orbiting around it. Maybe we know there's a planet there because we saw the planet in transit from a telescope like TESS. Well, just as that star tugs on the planet with its large amount of gravity that the star has, that planet will tug on the star. And because the star is much more massive than the planet, the tug that the planet exerts on the star won't make it move as much as the planet orbits around the star. But both these objects are orbiting around the center of mass of the system. So what that means is that this star is actually wobbling a little bit back and forth as the planet tugs on it. And so if we observe this star with a telescope, what happens is that wobble in the top right panel here, that wobble is being illustrated as the velocity of the star following this sinusoidal pattern over time. At some points, its velocity will seem that it's moving towards us, and sometimes the velocity of the star will be moving away from us. And observationally, what that means is just like an ambulance its siren might sound higher pitched when it's moving towards you on the street than when it's moving away from you. The Doppler effect will change the color of the starlight as we observe it. So just as this star is following this sinusoidal track in velocity, as it moves towards us, just like the ambulance, the starlight will be blue shifted. It will be shifted towards higher frequency, like the ambulance sounds higher pitched when it's coming at us. And as it's traveling away from us, the star's spectrum will look red shifted, or it will be moved towards lower frequency or longer wavelengths. And so we can detect this shifting of the light in various spectral lines in the star. And by measuring that wobble, you can measure the mass of the planet, because you can imagine a bigger planet, a more massive planet will induce a bigger wobble. Okay, cool. So That is like the 5 minute or 2 minute introduction on why radial velocities, what they are, how we make use of the observations, and why they're important. You can measure the mass of an exoplanet by using this radial velocity technique. And if you do it for transiting exoplanets, then that's very powerful, because now you have the radius of the exoplanet, how big it is, and you know how massive it is. So you can start to piece together, is this planet dense as the Earth? Is this planet very low density, like Jupiter or Saturn? And you can start to, snowball that into a million other questions about planet formation and evolution that we won't get into today. But that's the gist. We're using these observations to measure planet masses. Okay, so that's sort of the scientific motivation for you. But moving on to Radvel and some of the actual techniques we'll be using. We're going to first, I mentioned Radvel is a Python package that you can use to analyze these radial velocity data. And so we'll go through in this Jupyter notebook all the way from installing Radvel to testing it out on an exoplanet system with real data. So let's just skip right down to it. The install, I already have this installed on my machine, but it should be fairly straightforward. I would recommend you create a virtual environment, maybe a new virtual environment before you install Radvel, but you can install it from the command line using pip. You could also git clone the Radvel repository from GitHub. That would give you the most up-to-date version of the code. But however you want to install it, give that a shot once you're done watching this video. It should be fairly straightforward. There's some helpful information on the Radvel GitHub itself. We're just going to make some imports here. Now we're also going to get our hands on some actual data, right? We made those observations of a star spectrum and how it is red shifted and then blue shifted, and we translate those red and blue shifts into a velocity. Just like we saw here, we're trying to measure this curve over time. Okay, so what does this data actually look like? Well, Radvel, once we install it, actually comes with a little bit of data itself. So if we look at some of the data that Radvel has come along with, we'll see that it's in a nice and orderly data frame for us. It looks like we have, by printing out the columns of that data frame object, this panda, we're using pandas to read in a CSV file. We can see that the data here comes in, we have 3 columns mainly. It's the air vel, T, and vel. Okay, so that's not super useful without a header to explain what the columns actually mean, but for our purposes, this is just the error on the velocity measurement that we made, the time in some sort of, this is Julian day minus some sort of offset, and the velocity in meters per second of the star. And what we can do is, using our matplotlib skills, our panda skills, we can just plot that data here. This is just a time series. I'll leave some of these matplotlib little exercises for you to do as well. But yeah, here is essentially that data. It doesn't look as perfect and clean as this cartoon, but there's something here. There's something going up and down, it seems like. And you can see the x-axis is in time, and the y-axis is in meters, is in velocity in meters per second. Okay, so now we have some radial velocity data. What are some of the first things we should try to do when we're looking at it, right? Is there a planet there? If so, what's the orbital period of that planet? How many planets are there? How large is the planetary signal going to be? We don't know these things a priori. In some special cases, we might actually know about the planet's period from, say, a transit. But before we use any external information, one thing we can do is a periodogram analysis. And this is very important. Periodograms are can be a very complicated topic. You also might hear this sort of analysis referred to as Fourier analysis. Essentially, you're looking at time series data and trying to pick out periodic or quasi-periodic signals in the data. So how do we do that? Some of you may be sort of familiar with this technique before, but we can use what's called a periodogram to look for periodic signals in our data. And how that works is, if we look at this cartoon, imagine that on the left here, this red line is our time series data. And behind it, these three sine waves of different periods are, say, the underlying signal that if we sum up all these three signals, we'll get the red line. And so this could be like the radial velocity data that we observed right here. Maybe there's some complicated process. Maybe there's one planet, two planet, three planets that add together to create this kind of confusing looking signal that we see here. Well, the way a periodogram works is it's going to decompose this signal into a sum of a bunch of different sine waves at different frequencies or at different periods. And in that spectrum of sine waves, in that collection, that series of sine waves at different periods and different frequencies, you will see a spike in the coefficient of a periodic term when it contributes a lot of information to the underlying signal. So I guess what that means is on the right here, once we make the Fourier transform of this signal, we will see spikes at the specific periods that are making up the composite signal of our data. So yeah, it might be, I know Fourier transforms are still a little magical to me, even after all these years. So I would highly recommend, if it's been a while since you've thought about Fourier transforms or Fourier analysis, time series analysis, PhET actually has this great online simulation where you can add different sine waves together of varying amplitudes and see what kind of some signal you get out. So that might help you build some intuition there. Okay, so we're going to use this tool, a periodogram. In this case, it's called a Loam-Scargill periodogram, based on the people that invented this specific technique. So the first thing we do, this might be a good first step when you're looking at a radial velocity data set, is to just make a periodogram of the data. And if there are any giant spikes in the periodogram that you get out, that might be an indication that there's a strong periodic signal at that frequency, which in our case might be a planet. So we have this little function that we've used, we're going to use to generate a periodogram. I'm going to search, let's just say we'll search for periodic signals between 5 and, to start, let's make it 1,000 days, okay? I'm going to create my Loam-Scargill periodogram with my data. I'm going to tell it the minimum and maximum periods I want to search through. And for the maximum period, I want to plot a line and label it with this label to tell me what peak do I see in the data. Okay. And if I do that, it looks like there is a peak at about 20-ish days. Okay. It's a whole other business of determining, is this peak more significant than this one? What's going on over here? What about these small peaks? Do they matter? Do they not matter? That's something we probably don't have time for today, but for in the interest of just charging ahead, let's just zoom in a little bit. Okay, now I've set the max period to 100 days. It looks like there is this peak, yeah, at about 20 days still. So maybe that's where our first planet is hiding. Okay, so what do we do from here? We've used some periodigram analysis to identify what we think might be a periodic signal in our radial velocity data. Now is when this is when RADVEL comes into the picture. So RADVEL, if you're familiar with object-oriented programming, RADVEL is a great module for kind of cleaning up, making sense of all of your radial velocity analysis. RADVEL in particular centers around some objects called RADVEL parameters and models. And so what we're going to do is just build our model object and give it a bunch of different parameters. These parameters will include, for example, for one planet, here are some of the parameters you might be using. The period of the planet, that's important. That's like what we just tried to find out here, like 20-ish days. Also, TC, or the time of inferior conjunction. This is the point at which the planet, if this was a transiting system, would pass in between the Earth and the star. And also some other parameters that would define the eccentricity of the orbit. And then lastly, this is the radial velocity semi-amplitude. It's also used, we use the symbol K most of the time to label this parameter. And that is, like, you can imagine the height of the sine wave in this cartoon. Okay. So this will be our initial model. We're going to use the period from our periodogram analysis as an initial guess. We're cheating a little bit here because this system, K224, is known to be transiting. So we sort of know what the time of, we already know what the time of inferior conjunction is. So we're going to use that here, but you could equivalently make a guess and then use some sort of Y prior on it. And we're also going to make a guess about some other parameters. These are possible longer-term trends that we might observe in the data, specifically any curvature to the data, like a quadratic term in our model, as well as a linear trend. Okay. And so let's see, these are also instrumental parameters. You'll see this a lot in radial velocity analysis. Each instrument, each spectrograph that's used to collect radial velocity data will need a different offset term and a different, we call it a jitter term. And the jitter term kind of encapsulates some of the systematic error and uncertainties that go into observing. Okay. And so we're going to now plot the model with our initial parameter guesses. Okay, so right, again, this is time on the x-axis, radial velocity in meters per second on the y. The data's in blue, and the model, our initial guess for it, is in orange. That doesn't look super great, but what we can do is what's called a maximum likelihood fit. And so we're going to generate this RADVEL object called a posterior object, and we're going to send it essentially our likelihood object. So this, if you're familiar with Bayesian analysis or Bayesian statistics, this is all, RADVEL is all built in a Bayesian framework. So we defined what our model should be, we defined our likelihood function, some priors, and now we're going to condition our model on the observed data. Okay, and so we are going to, I'm going through this quickly because I want to get as far as possible, but we're going to now optimize our model given the data. And this looks like a much better fit. Okay, cool. So now here is the same plot, but you can see that our model is kind of snapping to the data once we've optimized all those parameters. And it does, RADVEL does come equipped with some fancy built-in plotting tools. Like this plot is like a publication-ready plot almost. And so here is our time series of data. Here is our quadratic trend and linear trend as well. And then below, this is what's called a phase-folded plot of the data. If we take the data and fold it to what we think the period of the planet is, in this case about 20 days, what does the orbit look like? For a circular orbit with 0 eccentricity, we'd hope to see a sine curve. Yeah, so I think I'm not going to have time to go into all of the rest of the notebook, but it should be fairly self-explanatory. What you're going to do now is another kind of common step in radial velocity analysis. Okay, now that we've found one signal in the data, maybe there are others hiding in the data as well. So we're going to take the residuals of our model, and we're also we're going to plot them up first, okay? And then we're going to do our periodogram analysis again. Are there any peaks in the residuals that we haven't identified? Maybe there's one at about 55 days. And then we'll add a second planet to our model, optimize it, and see how it goes. Yeah, the last section of this notebook is potentially the most exciting. Or the coolest. I think it's really cool. Markov chain Monte Carlo. This is, you'll notice in these fancy plots that Radvel generated for us. Okay, it says we have a planet at 20 days. The amplitude is 5.5 meters per second, and the eccentricity is 0.4. But there's no error bars on any of those numbers. So in science, we always want to be able to, if we give an estimate of a number or a parameter, a physical parameter, we want to report also our confidence on that parameter. And the way we do that in many cases in a Bayesian framework is with a technique called Markov chain Monte Carlo. So yeah, this is also covered in some of the background material, and the code should be fairly ready to run out of the box. So yeah, I definitely encourage you to download the notebook and give this a try.